Good morning and welcome to the NPTEL course Advanced Distribution System Analysis and Operation. We are continuing with our module 4, which is Distribution Network Optimal Power Flow Analysis. So, in the last class we have seen why we need a distribution network OPF analysis and how it is different from the transmission network, and today we will see different OPF control algorithms. So, first we will see the schematic of the distribution network OPF, abbreviated as a DOPF. So, the resources normally we have in distribution network, those are your upper grid, that means you have a connection with your upper grid and then your distribution network will start, right. This is your distribution transformer. So, this upper grid, that is a substation where you have connected your substation. So, that is the one source of your distribution network. Second, you have smart inverters that we have discussed with, that is with associated with the DERs. You have voltage regulators, you have battery banks, you have capacitor banks, you have solar energy, wind energy and switches. Switches we normally use, let us say you are trying to connect these two nodes and this is a normally open switch, and here you have a switch which is a normally closed switch. So, with the operation of these switches, that whether it will be switched on or switched off, depending upon that the architecture of your network will get changed. Okay? So, you have switches on all the DERs. Then the data exchange mechanism, comprising of the data exchange mechanism, your OPF can be of two types. One is static. That means whenever you will solve the optimization problem, that means you got your parameters, you formulate your problem, now you have fed that into your solution algorithm. After that, you fed it to the optimization algorithm, you have no provision to give any update value, updated data. That means whatever data you have given, you cannot update it. So, that is called a static formulation. But in case of dynamic formulation, which is very difficult to do, you can give a feedback or an interaction loop with your actual system, that even your OPF problem is under solution or you are solving it, in between that also you can send the updated information from your network, and that OPF problem has to accommodate it, has to implement it whenever it will take the next decision. Your problem can be of single phase or three phase, that we have seen. Either you can take balanced network for single phase or unbalanced network for three phase power flow. Your power flow model, either you can take as an SOCP relaxed model, you can take SDP relaxed model, linear model, or you can take branch injection model. That means either you can formulate your OPF problem with the help of BFMs or you can formulate with the help of BIMs. And accordingly, you can choose to eliminate the non-convexity associated with them. Okay. The time frame for your OPF can be of day ahead or real time. That means you can either formulate your OPF problem one day ahead, that means you are scheduling your network for tomorrow and you are doing the solution today, or you can do the solution now itself, that for your decision to be implemented after 1 minute or 5-minute time interval. That means let us say now you have, it is 12 p.m. and you are doing the solution for 12:05 p.m. That is called the real time optimization. Your algorithm can be of centralized, distributed, decentralized, hierarchical or local. Okay. So, what are they? We will discuss in the next slides. Your communication, obviously we are saying that data will be transferred to substation, data will be transferred to DNOs, you are sending data to the customers. So, without communication infrastructure, that is not possible. So, either your communication is synchronous, that means all the data are reaching to the control center together. So, that is called synchronous communication, or it is can be an asynchronous communication. That means multiple sources, they are sending data at their different clock time. Someone is sending at 1 minute time interval, someone is sending at 5-minute time interval, someone is sending at second time interval. So, if that is there, then it is an asynchronous data communication. The objective can be of cost optimization or minimization, loss minimization, profit maximization, voltage deviation minimization, conservation of voltage reduction. This is a CVR technique normally we used for the ZIP load model, because we have seen in the ZIP that if you reduce the actual voltage value, voltage magnitude value, then compared with your VR or nominal voltage value, voltage magnitude, then your total power consumption, active and reactive both, that will be reduced. So, by doing that you can implement conservation voltage reduction technique, or short form we call it as a CVR. But again, if you reduce the voltage too much, then what will happen? You will lose the system stability, or your network loss will be very high. So, there will be a trade off between your implementation of your CVR from your load reduction and your loss enhancement. Then you have minimization of the renewable power curtailment and minimization of the load shedding. Application is dispatch scheduling, economic load dispatch, load management, volt var optimization, network configuration and planning. This kind of application you will do with the DOPF. Now, we will see what are the OPF control algorithms or control schemes. First, let us say your system has multiple DERs or local resources, okay, or customers, whatever. Those are at the bottom of your network, or you can say leaf of at your network. Okay. So, if they are managing on their own, like your DERs or a storage, it is managing on its own to the schedule its charging discharging pattern. It is not communicating with any hierarchical operation, or it is not communicating with your DNO that when it should charge or when it should discharge. If that is the case, we call it a local control. Then if few of the DERs or few of the resources, they cluster together and they form an aggregator for them. Let us say these three, they clustered together and here is one local controller, these two they clustered together and you have second local controller. So, the decision for this local agents or LAs is decided by their corresponding local controllers. They will decide whether the local agent should operate or not and how much they have to operate. So, they will take consideration for these three together. Let us say for the local agent 1, it will take these three together and derive the solution accordingly. Similarly, it will take the decision for the 2. But if you take a centralized, this is called a decentralized one. Then the third one is the centralized. What is centralized? Centralized is that all 5 will come under one umbrella. That means your entire network is controlled by only one entity, that is the central controller or the distribution network operator. There is no middleman, no local controller present in the network. So, all the network resources which is present in your system, they has to report to the central controller through the communication medium. So, if that is there, then you will say we are doing the centralized control. The fourth one is the distributed control, where it says it looks like the distributed or decentralized control. It looks like a decentralized control where you have made a cluster that 3 will report to the local controller 1 and this 2 will report to the local controller 2, but previously you have seen, if you see, they are independent of each other in the decentralized control. These local controllers do not communicate, do not talk with each other, they are taking decision for their sake. But if you see for the distributed control, what you can see that these local controllers, they will communicate with each other for the sake of the benefit of the entire network. Okay. So, for the decentralized control, they are operating separately, but for distributed control, they will take their decision and they will convey that decision to their neighboring local controller. Okay. Then you have hierarchical control, which is a combination of distributed and a centralized control, where these local agents, they will report to the local controllers, but other than these local controllers communicating with each other, they will communicate it via a central controller, and that central controller will take the decision whether the local controllers are taking proper actions or not. So, these are the major 5 OPF control schemes normally we use. So, if you draw a comparison study between them, considering the few parameters like optimality, autonomy, resiliency, data handling needs and others, you see that local controlling algorithm gives you the lowest optimal solution, because you are taking decision on your own, you are not talking with anyone. Decentralized will also give you the lowest, because you are not operating for the sake of the entire network, you are just operating for your benefit only. Highest amount of optimality is guaranteed when you have a central controller in place. That means you have solved your problem as a centralized or a hierarchical manner. Distributed algorithm will give you a medium level solution. That means it is not a highest optimality, but it is not the lowest as well. If you see the autonomy, same, local will give you the highest autonomy, local and the decentralized, obviously, because you are the boss of yourself, you need not to report to anyone. So, that will give you the highest level of autonomy. The centralized and the will give you the lowest level of autonomy. Medium level of autonomy you will ensure in the hierarchical and the distributed algorithm, because you have a local controller there, right. You need not to give to the central, go to the central controller for the local agents. But if you see the resilience to single point failure, that means you have multiple communications, let us say this is your CC and this is your LA, this is another LA. If one communication fails, then your entire system will fail. So, that is why your centralized control has the lowest level of the resiliency for single point failure. That means, if one point fails, entire system will collapse, but your local and decentralized will sustain, because everyone is independent of each other. Again, medium level you will get with the distributed and hierarchical. That means, what is distributed? You have local controller here, you have local agents here, and then they are communicating with each other. So, let us say this communication fails. If this communication fails, still it can operate the system in a decentralized manner. Still your system will operate, it will not collapse down, right. Then data handling needs, obviously highest level of data you have to handle for hierarchical and the centralized, because the central controller has to handle the entire network's data. Lowest is for decentralized and your local, and medium for distributed. Communication requirement, it is very high for your hierarchical and the centralized, because a long communication infrastructure you need to send all the data from the lowest level or at the grid edge level to the central controller level. So, if your customer or if your DER is placed almost 20 to 30 kilometers away from your main substation, then you will need a 30 kilometers long communication channel dedicated that will send the data from the DERs to the central controller. So, you need a highest level of communication that is not needed for local and decentralized, because your data handling is done at the local level or at the lower level. Again, medium is level of communication is required, because you have only one communication at the local controller level for the distributed. Computing resources, you need a highly configured computing resources or computer to solve the centralized and the hierarchical control, okay, because you have to process huge gigabyte or terabyte amount of data. But for local, you do not need that much of data. If it is a small, only one battery, data is very small. If it is 2 battery, little bit of larger, but still it is compared to 1000 batteries connected to the central controller, it is very less. Again, medium level you can assure for the distributed. So, you can see that the distributed algorithms will give you a trade off between your local decentralized and the centralized hierarchical. So, if you cluster that your centralized control and your hierarchical control at the one side and your local control and your decentralized control at the other side, then your distributed control is somehow trade off between both of them. It takes the good point of both of them and somehow the bad points also of both of them. So, this is a very promising algorithm generally follows, that will give you a medium level of optimality and as well as that will give a medium level of independence as well. So, now we will move forward with the mathematical formulation of the OPF problem. So, designing optimization frameworks for performing optimal power flow study of active distribution networks is a challenging job. Why? We discussed that because of this nonlinear characteristics of the multi-phase formulation, right. Then that is why your OPF is mostly a mixed integer non-convex programming. Non-convex, that is clear. Why that is mixed integer? Because we have tap changing, that is an integer. You have switch status, that is also an integer, or rather say that is a binary. So, this variables you have. So, that is why it is a mixed integer non-convex programming. To find the optimal power flow solutions with lesser computation time, three different types of solution algorithms are generally illustrated in the literatures to solve this MINCP problem. First, you linearize all the non-convexity and solve. You can use the heuristic optimization or search algorithms, or you can convexify your problem and then solve the convex optimization. So, depending upon that, your problem, your OPF problem can be structured in two frames. First frame is that use the bus injection models, and second frame you use the branch flow models. So, the bus injection model says this model formulates the OPF problem using power injections at each bus as the primary variables. This will take, if you have a bus like this, it will take Pi and Qi as the variable. Okay. It is based on the Kirchhoff's current law, what we already derived when we derived the bus injection model. It is suitable for compact modeling, but leads to highly non-convex formulation due to the use of complex power and voltage variables. Okay. You can again model your OPF problem as a branch flow model, where we take the voltage values and the currents and the power flows in the line. That means, if this is I, this is j, we take this Pij, Qij, Vi and Vj as the variable, right. So, that we take for branch flow model. We have seen that branch flow model. It uses Kirchhoff's voltage law, and it is more natural for the radial distribution network, because in radial mostly if you do not have a DERs at the downstream node, always your voltage will be reduced, right. So, if you deal with this power flow, then you can say that at which direction your voltage reduction is there. So, it is very good to validate the problem. That means, if you see that power is flowing from Vi to Vj or I to j, then obviously your Vi is greater than Vj, that is the physics. So, that is very easy to validate the solution, whether you are getting an ACOPF feasible solution or you are getting an infeasible solution. Offers a clearer physical interpretation of the voltage drops and the losses, just I told, and it is better to suitable for the convexification, SOCP and SDP, that we discussed in the module 2. So, this is the overall nonlinear programming with the bus injection model when you want to reduce the total loss. So, the total loss is the injection of the power at all the network, all the buses. That means, let us say this is your bus I and this is your bus j. So, from here how much power you are sending and here how much power you are getting, that Pi minus Pj will give you the P loss. So, somewhere it is positive, somewhere it is negative. So, if you do that summation, then you will get the P loss. So, that we considered as the loss function, and this is your power balance equation, that is your active and reactive power balance equation. We have studied all this. You have voltage limit, your voltage magnitude must be within a certain limit, that is 0.95 to 1.05 per unit, that has to be satisfied, and your DR reactive power support from your DRs has to be also within a certain limit. That means, either it will absorb or it will supply, depending upon the situation how you are operating your network or what is the loading condition. So, if you formulate with the nonlinear programming branch flow model, you will see that the loss is now I square R for the current flow, Ij square R. That means, if you have an I and jth bus, if the current is Iij and the resistance is Rij, then your loss is I square R. So, this L is actually your I square, right. So, with this you can write, this is your actual voltage equation we studied, this is your power balance equations, these are the nonlinear equations. So, we took nonlinear equality constraints quadratic for relating the power with the voltage and the current. Then you have this V square constraint as well. That means, if V is less than equals to 0.95 less than equals to 1.05, then this will be 0.95 square to 1.05 square. So, this constraint we have to take, and similar again the DI reactive power constraint. So, why you need of simplifying this NLP, BIM and BFM method? Non-convexity makes the global optimization hard. The SOCP problem includes nonlinear power flow equation leading to non-convexity, which makes the finding the global optimum computationally challenging and also time consuming for very large systems. Then convergence and the optimality cannot be guaranteed if you go with the non-convex solution. But if you go with a convex relaxation, that will ensure the convergence to a global or near global optimal solution with strong theoretical guarantees. We have seen that if you make it less than equals to with the SOCP relaxation, then your solution will be convex and you will get only unique solution all the time. So, theoretically it is a guaranteed solution. Again, if your network is radial and R by X ratio is high, then it is an exact as well. So, you will get global optimal solution as well. It enables the use of different solvers. Whatever commercial solvers we have in our market, that commercial solvers are generally designed not to solve non-convex problem. They are generally designed to solve linear programming or convex programming. And then you can use those solvers to get the faster solution, and then you need not to do any heuristic or iterative methods that will take large time to converge, even that may stuck to the local solutions. With this, that will improve the scalability and the robustness. That means, if you model your network or model your OPF problem linearly or convexify it, then you can do it for the large system. Otherwise, if you go for the non-convex, then already you have multiple variables or very huge number of variables for a small system. Now, imagine you go for a 8000 bus system, that will, your volume of that problem will become very big. So, that scalability you will get if you go with the non-convex optimization. So, with this we have implemented this BIM model. If we implement that and we use those constraints as the power balance constraint and your voltage constraint, then you will get the linear programming bus injection model. Okay. The other constraints are same, only this voltage constraints had been changed because we are now doing with the del of or perturbation of the voltage from the actual nominal value 1 per unit. Similarly, cone programming you can do for bus branch flow model that we have studied for single phase power flow model. We are reducing the loss subject to the power balance constraint, your voltage constraint, your equality constraint, quadratic equality, which can impose the non-convex, but you can change that with the SOCP relaxation to an inequality. If you do that, then your OPF problem will become a convex problem. Okay. Again, for your 3 phase unbalanced network, what you can do? You have your loss problem. So, this current now you have to get rid of it. So, for it you can replace this current value with this expression of your power, and we are considering that the separation of the phases. That means we are considering 3 phases separately. So, if you put that and consider that the voltages are nearly close to 1 per unit, then your objective function will be changed function. Then you will replace this Lij with this Pij square and Qij square, what we mentioned here, with the subject to the linear constraints of your 3 phase model. So, that is why it is called, because you have quadratic objective at the objective function, quadratic function at the objective function, but others your constraints are linear. So, this formulation is named as quadratic objective linear programming branch flow model. This is easier to solve compared whenever you have quadratic term in your constraint. If you have quadratic term in your objective function, the solution of that problem is comparatively easier other than you have quadratic terms in your constraint. So, we have done a case study on IEEE 123 bus test system for this NLP-BIM, NLP-BFM, LP-BIM and QOLP-BFM. This is 123 bus system which has 123 buses, 267 single phase nodes and 253 single phase lines. We have perturbed or we have modified this network by placing 10 3 phase DERs, mostly we consider the PV inverters, of 50 kilowatt rating having inverter rating of 60 kVA, okay, and those are 3 phase. So, you have total 30 single phase DERs connected in the network. The substation voltage, this is at 1.04 per unit, the bus voltage limit is 0.95 per unit to 1.05 per unit. So, we are trying to minimize the loss of the network by determining the 30 DERs reactive power support. That means, we will determine how much Q support we are getting from the DERs, that will minimize the total loss of the network. We have solved it in a 32 GB i7 9th generation computer, and you can see the average voltage profile of the network for different algorithms. Okay. So, this OpenDSS is used to validate whether your solution is close to the actual solution or not. Okay. So, if you can see that with the LP-BIM, your voltage values are quite deviated. Okay. That means, LP, I already mentioned before that BIM model is not good for your radial distribution networks, that you have already seen theoretically. Now, you can see from the result as well that if you take the BIM model and then if you implement also linear programming on it, that means you are approximate it further, then your solution will diverge from the actual solution significantly. That we can see from this solution as well, that if your actual solution from the OpenDSS, which is a good solution, that is 46.95 kilowatt for the loss, you are getting almost 1 kilowatt more loss if you use the nonlinear programming of the bus injection model. For NLP-BFM, what is a branch flow model, that is actually been solved at the OpenDSS, that model is quite accurate and that model is more relevant for the radial distribution network, and you can see the solution is close to the OpenDSS solution. Similarly, LP-BIM will give you more diverse solution or more deviated solution, and QOLP-BFM, that is also giving a close proximity results. So, whenever we will do solve for the radial distribution network, we always choose between NLP-BFM or QOLP-BFM. Okay? This BIM solutions are not that much accurate for the radial distribution network, that we have discussed previously theoretically, now we have seen it practically. Solution time is also very huge for your BIM, because you have sine cos functions. So, that is taking almost 16.5 minutes for solving only for one time instant, you take only one shot, right. For nonlinear programming BFM also you are getting almost 9 minutes time to solve it, but you can see if you do the linear version, your solution time has reduced significantly. Even for LP-BIM your solution time is the least, but for QOLP-BFM it is little bit more. Why? because your objective function is still quadratic, but that time gap is insignificant. Okay. So, we can see that this QOLP-BFM is a good algorithm if you want to solve the radial distribution network. So, with this I will end today's lecture and we will continue with this formulation part in the next class. Thank you.